Mass spring damper. Where's the damper?
I don't know, but I googled it and it
Oh,
said it would work.
I didn't know.
I finished all of it. Mark is arguing for everyone, and then I typed all of my SCIs at the end.
Good thing we got on tape. Just how crazy stuff. Yeah, look. Mass spring damper. A zipper.
You know what a mesh string damper is?
Yes. Look at the suspension in the car. Yeah, but I said you can't use anything like that you said. That's the first thing I thought of.
Yeah. So what's the problem?
Yeah, I can't think of any other system.
Why do you want to use the other system?
Huh? That's
That
that?
has springs in it.
Oh, that's mine.
Yeah, because I already have mine.
Wait, you have to have a different one for each one of us?
Yeah.
I mean, you can just.
I have a bunch of cords.
I have a trampoline. So you can.
Wait, when did you
He took the whole mix too. No, he just don't make it like the latest, like the one you get.
I'm gonna use
What if we all put the exact same thing? Everybody in the car.
what if I need one?
You get it out.
Scan?
Yeah. See? Nope.
I
Yeah, had a note.
can't do anything not really.
Yeah, there were notes. There were notes.
What is that? Bridge?
Bridge.
Self-destruction or what? What am I gonna do?
I shut up.
I can do a system.
Five cents.
That doesn't have spring. I mean, it does.
5 pages long.
I can do a valve.
So what would be the damper in this one?
What about like a thing that pushes like cans down?
Hydraulic press?
Yeah.
That's not hydraulic.
Oh, well then there's something else that pushes cans down. Oh wait, what are those things called? Pliers.
What?
Pliers.
Pliers?
Isn't that something that you put down on? Pliers? Yeah, pliers. Tweezers too.
No,
But
that's
tweezers don't have springs.
different.
No, it's pliers. The one
Okay,
with all the
good morning everyone.
Springs have to be advanced. They have to exist.
Alright, so we'll continue with what we've been doing so far, plane stress and looking at material failure. I have uploaded your pre-lecture notes with the figures necessary for today's class, so you can pull it up. It's on Notability as well as the PDF. Alright, I'm going to give a brief summary of what we've seen in the past two classes, and then we're going to come up with a graphical technique for finding whatever we did. We did a lot of derivations, right? We were slicing the plane, then writing components of the force and so on. And that's for a very simple situation of loading. If the loading situation is much more complex, then it becomes much more complicated to do the force balance and so on. So we have to resort to what is called as a graphical technique, which is the Morse circuit. Okay? So, but before that, a brief summary. Two types of material failures that we typically notice: ductile material failure, brittle material failure. Okay, so ductile. Ductile failure, experimentally determined, it happens due to maximum shear stresses. Brittle material failure, on the other hand, occurs due to maximum normal stresses, which are typically called as the principal stresses. So brittle failure. This is due to maximum normal stresses. The maximum normal stresses typically are called as the principal stresses. And the fundamental thing that we've been seeing so far is that for certain problems, it is not necessary that the plane of failure be the same as the plane of loading. So they could be at an angle with respect to each other. Okay, so plane of failure. Which contains the principal stresses or the maximum shear stress depending on the type of material failure, is not necessarily the same as the plane of loading. In certain cases they can be the same. You're going to see that too today. Is not necessarily equal to the plane of loading. They will be, most situations, at an angle with respect to each other. Depends on the type of loading. Okay? And we looked at two types of loadings. One was a purely tensile force acting on a specimen. The other one was a torsional loading, piece of chalk, apply a torque, fractured at an angle. So I'm just briefly going to summarize those figures for us. So first one is tensile loading, so pure axial loading. This is the simplest type of loading, okay, for any kind of a body. Just take a force, we pull it. That's about it. And for this I considered a specimen of the following nature. Okay, so this is the plane of loading for that particular specimen. I have not specified whether it is ductile or brittle for the time being. Plane of loading. Apply a force. Force P. Area of cross section is A. I set up a pair of axes, x-axis, y-axis, z-axis, x-axis along the axis of symmetry, y-axis, and then the z-axis is the other planar axis, the z-axis. Usually what we do is, we will figure out, as we mentioned last time, we have to figure out a critical location. Here any location can be critical, because the normal force or internal normal force at any location is the same. So I would slice it open at some point. Okay, so slice it open, break it up into two pieces. I'm still looking at the plane of loading. This is the plane of loading. I take the piece, force P. I draw an area element and depict the state of stress on that area element. So somewhere here. On that area element, obviously on the plane of loading, the state of stress is going to be a normal stress, which is sigma xx in this case. This is my x-axis, my y-axis. Z-axis. All of these figures are there in the files that I have uploaded on Carbon. Sigma xx is going to be the value of the stress on that particular area element. I can take that area element, and sigma xx obviously is a force P divided by the area A, right? This is common sense, because there is no other load present in the problem. Okay? Then I take that out and draw it as a volume element. Okay, so that's the next step. Right, so here is my volume element. On the face that I see, I have a sigma xx on the back face, equal and opposite sigma xx. All of this is on the plane of loading. Okay, so this is still the plane of loading. So far this is all old news, right? This is something that we've seen before. But what we are seeing now is that I can impress upon this problem a plane state of stress by setting up my axis system, y-axis pointing vertically up here, x-axis, and my z-axis. So I can view it with respect to the perspective of the z-axis so that I get an xy plane. So this is my viewing perspective. And if I do that, and I tilt it towards you, you're going to see a rectangle. And on that rectangle, I'm going to have the x-axis and the y-axis. And along the x-axis, I'm going to have sigma xx, which is the force by the area. Okay, so this is a plane state of stress, obviously, because there are no stresses on the out of plane direction. This is all with respect to the plane of loading. And now we make the judgment call. Okay, is your material brittle or is it ductile? If the material is brittle, what happens? Right, we saw this last time very briefly. I have a piece of chalk, which is a brittle material. I take this piece of chalk and I just apply a uniaxial load. Just pull it apart. Plane of loading, flat. Plane of failure is also flat. Plane of loading is coincident with the plane of failure. Brittle material fails because of maximum normal stresses. So on the plane of failure, which is this nice smooth cut that you see here, the maximum stresses will be the normal stresses, and they will in fact be equal to the value of sigma xx. Okay, so for a brittle material, I'm going to have the axes now as the principal axes. They are coincident with the plane of loading, so I'm going to call them as 1 and 2. If I look at the plane of fracture, this is the plane of fracture. It is the same as the plane of loading, or it is coincident with the plane of loading. Okay, so plane of fracture or failure. Am I making sense to everybody? This is for a brittle material. Okay, so all I'm doing is drawing the state of stress on the plane of failure, which is going to be the same, exact same thing as the loading situation, because the plane of failure is coincident with the plane of loading. And my stress will be sigma 1, sigma 2, sigma 1, sigma 2, but there is no sigma 2 here because this is uniaxial loading, so sigma 2 is actually 0 for me, and sigma 1 is equal to the sigma xx value, which is P by A. This is equal to 0. On the other hand, if I have a ductile specimen, then I know that if I apply a tensile force on the ductile specimen, the plane of fracture is at an incline. Okay? We have seen this. This was 2 lectures before. So please go back and refresh your memories in that situation. But if I have a ductile material, for this particular plane of loading and for this particular situation of loading, I'm going to have the plane of failure tilted with respect to the plane of loading. The failure is due to shear, which means that on the plane of failure I'm going to be seeing shear stresses, and as we saw a couple of lectures back, there will also be a normal stress which is the same in all the directions. Okay? So here I'm going to see a shear stress. And also normal stresses. plane of failure. I have the plane of loading. The plane of failure is at an angle to the plane of loading. Okay, and this shear stress value, as you would know, so this is tau. This is sigma average is the normal stress on all directions. It's the same in all directions. This is also sigma average. Sigma average. This is tau, and this is tau. And this is also tau. Plane of failure, plane of loading. They are at an incline with respect to each other. And interestingly, maybe I'll have it in the next slide. Can I pull the board up for everybody? And in that situation, the value of tau we found out was half the value of the actual force that was, the stress that was applied in the loading plane. So for ductile, tau was P by 2A, and the inclination was 45 degrees as we know it. Okay, so this was equal to sigma 1 minus sigma 2 by 2. Can you all relate that to each other? Sigma 2 is 0, sigma 1 is P by A. If I take sigma 1 and sigma 2 divided by 2, I get P by 2A. So this is the relationship between the maximum in plane shear stress and the principal stress. So this is maximum in plane shear stress. Okay. And so tau max in plane is sigma 1, sigma 2 by 2. We are doing a two-dimensional state of stress, so which is why I'm talking about an in-plane shear stress. In 3D things will be a little different. Okay. I will not be going there for this particular class, but if you're taking machine elements and so on, later in the future you'll be seeing 3D states of stress, where we will be looking at how these things change when you go to 3D. Alright, so this is all for a tensile state of loading. If I have a torsional load, what do? Same thing, in many ways. Okay, so if I have pure torsion, I'm going to slide this up a little more. If I have pure torsion, do the same thing for a brittle material and a ductile material. Once again, this is a recap of what we did in the last lecture. Okay. These are my planes of loading. On both sides I have a torque applied. Right hand rule, positive torque. Okay, I set up the same pair of axes, x-axis, y-axis and z-axis. Z-axis. Plane of loading is what you're seeing here. Area is A. This is the second simplest type of loading that you can have. Most problems, as you know, we have been doing combined loading, where there are forces in all directions probably. There are bending moments, there are shear forces, there are normal forces, there is a torque applied. So how do you siphon out what is the failure values of the stress? That's much more difficult, right? You can't just do a force balance and get it. It's quite painful that way. So I cut this open because the internal torque is the same throughout the length of this bar. Cut it open, draw the cut portion. is the torque T. The internal torque is going to be equal and opposite to that. Is equal to T. I choose a point on the outermost circumference of this shaft because that's where the shear stresses are the largest if you have a torsional load. Select some convenient point. And if I draw the state of stress at that area element, it's going to be a shear stress pointing vertically down, tracking the direction of the torque. This value is equal to tau. Okay, this is once again on the plane of load. I take that area element, make it into a volume element. Same steps that we've been following so far. Right, so here's my volume element. On the front face I see a shear stress, on the back face I see a shear stress. Top and bottom also I will be seeing shear stresses. Vertically down, this way, and on the bottom face. These are all the same values of shear. This is a state of pure shear. As you can see, there are no other stresses produced. And this is the complementary nature of shear stress. A shear stress on one face will cause a shear stress on the back face. The shear stress on the two faces will cause shear stresses on complementary or 90-degree orthogonal faces, top and bottom. Okay? Once again, axis system, x, y, and z. So this is your y-axis. This is x-axis, z-axis. Set up a view so that I see a two-dimensional state of stress. So this is my view. Draw that rectangle. Mark the direction of the stress. First of all, draw the axes, x and y. On the sides, I have shear stresses pointing up and pointing down. All of you with me so far? Once again, a recap of what we've done, okay, just in terms of pictorial notations. And then, depending on whether the material is ductile or brittle, so we said that if it were a brittle material, piece of chalk, I have a torque applied, I will see that the plane of failure is not necessarily the same as the plane of loading. It's at an angle to each other. This angle we figured out as 45 degrees. After going through a lot of pain. Okay, so I take that guy, so it is going to be rotated at a certain angle if it's a brittle material. And if it is a brittle material, you will be drawing only the principal stresses, and the plane containing the principal stresses is always free of shear stress. We figured that out last time as well. We found out that the angle was 45 degrees, and when the angle was 45 degrees, the shear stresses vanished if it were a brittle material. So all I'm going to have is the two direction, the one direction. I'm going to have stresses in the one direction. And the two direction also will be having the same stresses as the one direction in this case. We did not show it in the last class, but believe me, it will be the same thing by doing force balance. So sigma 2, sigma 1, sigma 1, sigma 2. The value of sigma 2 and the value of sigma 1 will both be equal to the value of the shear stress tau. Okay, so this is equal to the magnitude of tau. And the nature of the failure obviously was at an angle. Okay, so they are at an angle with respect to each other. So this is what is the case for the brittle material. For the ductile material, we did not do this, but you can take it from me. Because of the fact that the loading is shear, the failure has to be shear as well. Because ductile materials fail by shear. So if you take a large shaft made of steel, and if you have the strength to twist it and cause it to break, if it's a ductile material, which steel is, the failure will be a clean, nice plane which is the same as the plane of loading. Okay, so don't do this, of course, but you can see tests where they perform a torsional failure. You twist it, the plane of failure is going to be exactly clean and smooth as the plane of loading for a ductile specimen. So for a ductile specimen, sigma average, and this is tau max. Tau max, plane of loading, plane of failure will be the same. This is for a torque. Likewise here. This is for a ductile specimen. Okay, the tau max value will be equal to tau. And the value of the average stress will be equal to half of tau, magnitude wise. And you'll see why and how when we do Morse. Okay, it's much more easier to understand that way. So out of these figures, the figures that we saw were for a brittle material under torsional loading. This is what we saw in the last lecture. And then we also went through the ductile value for a purely uniaxial loading, the lecture before that. What is the use of what we are doing? It helps us understand material failure. We looked at the simplest cases of loading and we figured out that after a lot of song and dance, we can obtain what the maximum shear stresses are, but that's after doing a lot of work, a lot of math. So rather than go through all of this math, there is a much more simpler, much more elegant technique, which is a graphical method, which will give you the exact same answers without doing too much of work, which is what we like to do in life. Okay? So with that said, I'm going to erase this board, the first panel at least, and I want to talk about one more thing before I go to Mohr's circle. I want to give a general plane of loading, plane of failure, and some angles and so on. I want to talk about that. So in general, plane of loading and this is for plane stress, so I want to make that clear. For plane stress, the plane of loading, the general state of stress will be shown in the following sign convention, which we also went through last time. X-axis, y-axis, typically called x and y-axis. There is nothing, nobody is wedded to this convention. You can call it y and z as well if you want, but it's convention to call it as x and y. On the side that has the positive area normal, the shear stress will be chosen to be positive, pointing up. And once I have the direction of that creature, I'm good to go. Everything else comes out perfectly. So this is tau xy. In our problems, we may or may not have a tau xy. If I had a purely uniaxial loading, tau xy was 0 for me. If I have a pure torsional loading, tau xy is equal to the shear stress tau due to the torque apply. This is for a general state of loading. I'm going to have the normal stresses, sigma xx, sigma xx, yy, sigma yy. Okay, so this is from a given problem. If I am finding principal stresses, it is possible that the principal plane may be tilted with respect to the plane of loading. So in the next panel, I'm going to draw a generic state of principal stress. So generic principal stress. This is for plane stress. The principal planes will be typically labeled as, the principal axes will be labeled as 1 and 2. Okay. The tilt between the one axis and the x-axis this as the x and the y axis, the angle of inclination will be called as theta suffix p. P standing for principal plane. This is in general. That's what you would have seen here in this case. For the brittle material, what is theta p? Theta p is 45 degrees. And sometimes people will say, okay, this is from x-axis to the one principal direction, so this is theta p1. If I go from x-axis to the two principal direction, it's theta p2. Okay, so that angle is theta p2. Along the 1 and 2 directions, I have the principal stresses. Sigma 1, sigma 1, sigma 2, sigma 2. This is free of shear stress. Okay? Principal plane. Extremely important to understand. We derived it as well for the brittle material. At the maximum angle of fracture, 45 degrees, the shear stress has vanished, which seemed kind of spooky, but that is the truth. Okay? Then we will also draw the general maximum in-plane shear stress and plot it out here, and then we'll go to the Mohr circle idea. Alright, so maximum in-plane shear stress. This is once again for a plane state of stress. And as we saw last time, there are two approximations you can make for material behavior. Plane stress for very thin bodies, plane strain for thick bodies. Okay? I'm drawing it at some generic inclination. Here I call it as x prime and y prime. I also use x s and y s, but that's kind of confusing, or maybe I'll just use x s and y s rather than x prime and y prime. Forgive me. X s and y s. Okay, so this is the direction for the shear. And I'm going to have tau max, tau max, tau max, and tau max in plane. This is the maximum shear stress on the plane of the problem that I'm envisioning, on this situation in the xy plane. Remember, there are three planes, the xy, the yz, and the xz plane for a typical problem. So it is possible that the tau max in plane that we are calculating using the plane stress approximation is not necessarily the largest shear stress. because that could occur on any of the other two planes. Who knows? God knows if there is a God, right? So keep that in mind. This is only for a plane stress approximation, a two-dimensional state of stress only. Okay? And then I have average stresses. Sigma average. Sigma average. Of course, they are the same in both the directions. So sigma average. Average. Max in plane. And likewise, and the inclination with respect to the x and the y axis. Typically, this angle will be called as theta s for shear. But since I'm going from x to the first xs axis, this is typically called as theta s1, and then theta s2. Okay, so these are all generic. And I want to see if there are any broad questions on what we've done so far. Give everybody some time to catch up on writing stuff. All these figures are there in your notability file, so yes. Not all the time. Depends on the type of loading, depends on the type of material. In this situation, when I have, for example, the brittle material under pure shear, theta S1 is 45 degrees. I mean, theta P1 is 45 degrees, and if I have a ductile specimen under pure axial loading, theta S1 is 45 degrees. Okay? It's not necessary. This, yeah, I need to maybe mention that also. Not always 45 degrees. And likewise, this is also not always 45 degrees. When can it be 45 degrees? If I have a brittle material and if I am subjecting it to a torsional loading, then theta P1 is 45 degrees. Or if I have a ductile material and I am subjecting it to a purely uniaxial state of loading, that theta S1 can be 45 degrees. Okay? So which is why, because of the fact that if you have a generic state of loading, I don't know how to calculate these angles, you make use of a graphical technique. It's much more simpler. I'm going to get rid of this particular panel here. Yes, question? Okay, can you say this again, please?
In the maximum plane, can you just explain the direct relationship between the sigma average and the max?
Sigma average is typically just going to be whatever is the average value of the principal stresses. So this is usually going to be sigma 1 plus sigma 2 divided by 2. And this is going to be tau max is sigma 1 minus sigma 2 by 2. Okay, so that's the relationship between the two. So if you want to make that note here, so tau max in plane is sigma 1 minus sigma 2 by 2, and sigma average is sigma 1 plus sigma 2. So I guess what I want to say is for all problems, it is sufficient if I find the principal stresses. If I know the principal stresses, I know everything about the failure depending on whether the material is ductile or brittle. If it is ductile, I can calculate the shear stresses that cause failure due to the principal stresses. If it is a brittle material, I already know the principal stresses, I don't need to go anywhere. Okay, so the key is to calculate the principal stresses. Okay? Alright, so I'm going to go to the Morse circle method. And here's what we are going to do. I may not get to a problem today, but I'm going to outline the idea of Morse circle, tell you how to draw it. Tomorrow during recitation, your TAs will solve two problems. It may or may not make much sense, but just go with the flow of how to draw these circles and obtain the information. On Friday, we'll come back and solve a problem from scratch. Okay, this is just to get you used to drawing Morse circle. Alright, so Morse circle. What we are drawing is a 2D Mohr circle. There is also a 3D Mohr circle which we will not be doing. Because we are looking at plane stress, we are limiting our viewpoint to 2 dimensions. But it's a good starting point for many material behavior, or many loading behavior, not material behavior. This was a graphical method invented by Otto Mohr. Graphical method to obtain principal stresses. And maximum in plane shear stress. Otto Mohr was a civil engineer working for the German railways, and I think around late 1800s is when he came up with this technique of drawing circles and orienting them so that the planes of failure would be very easily obtained using his technique. Okay, so this is a graphical method. Its basis is on equations, which we have seen a little bit of. Okay? Alright, so here is what you do. You start off with the generic state of loading on the plane of loading. I'm going to get rid of these panels here.